back, I should say, to many of you who were here yesterday. Today, we're celebrating chemistry. The Academy met in session this morning, took the decision on the Nobel Prize in Chemistry, and we have just spoken to the Nobel laureates. I'm Göran Hansen, I'm the Secretary General of the Academy, and with me today is on my right, Professor Claes Gustafsson, who is the Chairman of the Nobel Committee for Chemistry, and on my left, Professor Sara Slobe-Lindsey, who is a member of the committee, actually it's previous chairman, and an expert in the field of this year's prize. And as usual, I'll read the announcement in Swedish and in English, and then the citation also in German, French, and Russian, to cover all Alfred Nobel's favorite languages. Then we'll hear remarks about the prize from Claes and an introduction to the science behind the prize by Sara. This year's prize is about harnessing the power of evolution. Årets pris handlar om att bemästra evolutionens kraft. Kungliga Vetenskapsakademin har idag beslutat att utdela 2018 års Nobelpris i kemi med ena hälften till Frances Arnold för riktad evolution av enzymer och med andra hälften gemensamt till George P. Smith och Gregory P. Winter för fagdisplay av peptider och antikroppar. The Royal Swedish Academy of Sciences has today decided to award 2018 Nobel Prize in Chemistry with one half to Frances H. Arnold for the directed evolution of enzymes, and the other half jointly to George P. Smith and Gregory P. Winter for the phage display of peptides and antibodies. Zu einen Hälfte an Frances Arnold für die gerichtete Evolution von Enzymen und zur anderen Hälfte gemeinsam an George Smith und Gregory Winter für das Phage-Display von Peptiden und Antikörpern. Pour moitié à Frances Arnold pour l'évolution biologique des enzymes et pour l'autre moitié conjointement à George Smith et Gregory Winter pour le phage display des peptides et antikörpern. Frances Arnold za naprawioную ewolucję fermentów, George Smith i Gregory Winter za fagowy display peptidów i antikörper. And on this slide you can see some brief biographic data about our new Nobel laureates. Frances H. Arnold was born in Pittsburgh, Pennsylvania in the United States in 1956, and she's currently at the California Institute of Technology, Caltech, in Pasadena in the Los Angeles area. George P. Smith was born in 1941 in Norwalk, Connecticut, and he's currently at the University of Missouri in Columbia in the United States. Sir Gregory P. Winter was born in 1951 in Leicester in the United Kingdom, and he is at the Laboratory of Molecular Biology at the University of Cambridge in England. So with that, I'd like to ask Claes Gustafsson, Chairman of the Nobel Committee, to make some remarks about the prize. Claes.
Thank you, Göran. So this year's prize in chemistry rewards a revolution based on evolution. Our laureates have applied the principles of Darwin in the test tubes and used this approach to develop new types of chemicals for the greatest benefit of humankind. In the natural world, evolution of proteins has been around for thousands of millions of years, all the way back until the start of life on Earth. Genes have mutated and proteins have evolved to improve the fitness of this life. For thousands of years, we humans have used selective breeding to create animals and plants with properties that have been useful for us. This year's Nobel laureates have taken the next step. They have used the molecular understanding that we today have of the evolutionary process and recreated the process in their laboratories, in their test tubes. In doing so, they have been able to make evolution many thousand times faster, and they have also been able to direct evolution to create proteins with new and useful properties. This work has led to the creation of proteins with new enzymatic activities, able to catalyze useful chemical reactions. In addition, with a method called phage display, they have also evolved proteins with new binding properties, such as antibodies, that can be used to treat disease. In their laboratories, our laureates this year have been able to direct evolution, to steer it, which has led to new chemical tools that can be used in everything from environmentally friendly detergents to the creation of new biofuels and pharmaceuticals.
Thank you, Claes. Sara, can you give us some insights into the evolution of enzymes and phages?
Okay, thank you. Life on Earth is the result of billions of years of evolution. Organisms have adapted their chemistry to fill niches and environments. Random mutations in their genes lead to changes in their proteins. Many of these are enzymes. Enzymes speed up the chemical reactions in biology. Any changes that are beneficial or do no harm may be kept for the next generation for further randomization and testing during generations to come. Evolution has given us an amazing variety of creatures, full of little helpers, enzymes. Chemists use enzymes to speed up reactions in their laboratories, in industrial processes, and in consumer products. Over decades, scientists have tried to improve enzymes using rational thinking. Frances Arnold realized that to really get somewhere, she needed to grasp evolution and blend in an element of randomness into the process. In 1993, she published the first example where she had used directed evolution to improve the performance of an enzyme. She took the gene for the enzyme, introduced random combinations of point mutations, expressed all these genes in bacteria that were then producing a whole library of enzyme variants. These were screened for activity, and the best variants were kept for further rounds of mutagenesis and screening until a desired level of performance was obtained. To the left, there is a model of the enzyme that she has optimized in green. The blue is the substrate. As the diagram shows, the best variant after 3 generations of random mutagenesis and screening was 255 times better, 256, sorry, times better than the starting enzyme. In red, we see the side chains, the positions of the enzyme that were changed to achieve this. Nobody could have predicted this, that this particular combination would do the job. This illustrates the power of evolution and the element of randomness. Frances Arnold has since used directed evolution to improve a number of enzymes for new reaction conditions, to conduct new chemical reactions, to take in new substrate, even to make bonds for which no enzyme is available in nature. The applications are numerous and include molecules used for brain imaging, biofuels, pharmaceuticals. The enzymes used from directed evolution make us a greener chemical industry where they can replace more harsh chemical catalysts, even toxic metal ions. Enzymes derived by directed evolution are also used to make high energy molecules and reaction intermediates for synthesis. Now over to the other half of this year's Nobel Prize in Chemistry, where we award the phage display of peptides and antibodies. Now we get to meet a new little fellow, a bacteriophage. This is a virus that can infect bacteria. A bacteriophage is a protein capsule that encloses the DNA that codes for its own makeup. It fools the bacterium to produce new copies of the DNA and all the proteins and spit out a multitude of copies of the infecting phage. George Smith realized that this could be used for powerful technology. He took a foreign gene placed it inside the gene of one of the capsule proteins, so that the encoded protein ended up on the surface of the particular phage. This we call phage display. In his first work, he displayed a fragment of a protein. This we call a peptide. And he mixed the displaying phages with a millionfold excess of other phages. And then he immobilized, in yellow here, the antibody that's specific for this peptide and used it to fish out the binding phages and wash out the rest. After this, he also introduced the concept of peptide libraries, where he displayed not a single peptide, but a whole library of different peptides or phages. And when he used the antibody to fish, he could then get the sequences with highest affinity for the antibody and determine its epitope. To really use the technology to derive therapeutic antibodies, the phage display has to be done in reverse. Gregory Winter took a fragment of an antibody, a fragment here in yellow that contains all the binding parts, and managed to display it in fully functional form at the surface of the phage. Again, he added a millionfold excess of other phages, and he could use the target of the antibody as a fishing hook to pull it out and remove the non-binding ones. He then went on to make libraries of antibodies on phages, and using an immobilized target, he could add a library, wash away the weak binding antibodies, extract the high affinity ones, and subject them to new rounds of diversification and screening to select better and better antibodies. And over just a few generations, he could obtain very high affinity and very specific antibodies. And this forms the basis for a pharmaceutical revolution. Antibodies produced by phage display are used to treat diseases such as autoinflammatory diseases, anthrax, and cancer, and many more are currently in clinical trials. The methods developed by Francis Arnold, George Smith, and Gregory Winter are to the highest benefit of human health. Thank you.
Thank you, Sara. I think we may now have one of our Nobel laureates with us on the phone. Dr. Arnold, are you there?
I am there.
Hello again. This is Göran Hansen. I'm the guy who woke you up in the middle of the night less than an hour ago. Have you had your cup of coffee yet?
Not quite yet. I can grab water on my table.
So we are sitting now in the session hall of the Academy of Sciences, and here are nearly 100 journalists in total, and I'm sure some of them would like to ask you some questions. So are you ready for them?
I am.
Shall we give Thomas von Heyde a chance to start?
Thank you. Congratulations, Nobel Prize.
Thank you so much.
We have a paper here with a headline that says "Playing with Evolution," and I was thinking maybe something similar has been said about what you do earlier, and sometimes a phrase like that could make you suspicious. What are you up to? What are you doing? Have you had lots of questions like that? And what do you usually say?
I do think questions like that because for curious.
Now we have some problem with the line, I'm afraid. Sorry to interrupt, but we cannot really hear you, Dr. Arnold. Let's see if we can do something about it.
Thank you.
Okay, let's try again. So please go ahead.
I have to just understand it's still
Okay, what a pity. The line doesn't work. So much for sophisticated electronics. I wish there were evolutionary developed enzymes instead. Yeah, no, I don't think we get anywhere. Want to give it another try? We can give it one more chance. No. They have to save their questions for when you come here in December. thank you so much for trying to be with us during the press conference, and we look forward to meeting you in December when you come to receive your Nobel Prize. Thank you and bye-bye. Well, I'm afraid you'll have to do with us in the panel instead, the lady over there. Will you wait till you get the microphone?
Sorry, could I stand up or just sit here?
Just sit.
Okay, thank
Please.
you. This is Janet Wang from Nordic Chinese Times, and we noticed that many of the Nobel Prizes in physics or chemistry during the decades have been awarded to the findings related to cancer, biology, or physiology these years. And so my question is, could I ask if why are these phenomena increasing these years, and what would the Nobel Prize Committee suggest in the future? Thank you.
I think we'll ask Claus Gustafsson to comment on that.
So there is no real intention from our side to sort of focus on these subjects that you bring up. But it could be true if you go back to that there can be some pattern there. I think it has to do with the fact that, Alfred Nobel, he wanted a prize that was for the greatest benefit of humankind. So it had to have consequences for people, for humans. And I think that because we are always looking at both brilliant science, but also brilliant science with sort of consequences. And maybe that's why you can see that some of the prizes are related to the area which you allude to.
Thank you so much. I think these findings are really inspiring and marvelous. Thank you.
Good to hear. Good to have you with us. More questions? Yes, the gentleman from Associated Press.
Thank you. So I understand that you spoke with the laureates. Would you be able to tell us a little bit how they reacted? Have you managed to speak to all of them, and how was their initial reaction when you told them the good news?
Yes, we spoke to all three of them, and they were all very happy and enthusiastic and exhilarated. They look forward to coming here in December, and they were also happy to share the prize with their colleagues. So it was all positive reaction. We spoke with Rick Winter first, then with Francis Arnold, and last with George Smith. They were all delighted. Yes, please, Per Starter.
I wonder if there are any patents in this field that have economic significance for pharmaceuticals or other products.
Sara, would you like to answer?
Yes, Francis Arnold holds a whole range of patents. Enzymes that make biofuels, for example. So you can now make fossil-free fuels for cars and airplanes based on our technology.
From what? From what substances?
From different grown substances. So it's not taken out of the fossil reserves. So renewable resources. I think she holds something like 10 to 15 patents. I am not aware of the exact number. Gregory Winter also holds patents for some of the antibodies that are derived by phase display technology.
Thank you. More questions? This is your chance. Yes, please.
Thank you. I'm Subian Asasong from Green Post and China Radio. I'm sorry, I'd like to ask you to use simple words to explain in short how significant their discoveries are.
I'd say very significant. I'll give Sara a chance to say something more.
Yes, if we start with the first half, the significance, one significant is that you can now use enzymes to speed up, in principle, any reaction you want using these protocols. And you can derive enzymes that replace previous toxic catalysts in industrial processes. I think it has a very huge significance. And the second half makes it possible to derive fully human antibodies using the phase display. These libraries are now composed of fully humanized antibodies from the start. So they can be adapted, and they can be made to be very high affinity and specificity, so that you can use very small amounts in treatment.
So perhaps via safer, greener chemistry and antibody drugs with better efficiency and less side effects. More questions? Yes, please, gentleman over there.
Are there any potential damages in these researches, like such as create super species, could be damage humankind?
Claus?
Should I answer? So there are, of course, with all science, there are of course risks. But when you think about the science that we talk about here, it's sort of heavily regulated by, it's gene-modified microorganisms and sort of, or used all over the world in different labs. And we use them today to produce things like insulin, for example, treating millions and millions of people. So this is that there is a rule-based system that is sort of well established and that regulates this work also. Then of course evil minds can always do things with technology, but I don't see any particular dangers with this price compared to many other things.
More questions? If not, thank you very much, and we'll close this press conference and there will be individual interviews. Thank you very much.